So good afternoon everyone and welcome to this lecture. This is the last lecture before your exam. So we will be winding up this chapter and solving problems based on this. The chapter is magnetic effects of current and this is the last lecture, lecture number 12. What did we see up till now? What was the topic that we did in the last class? Anyone remembers? What did we do in the last class? No one.
Magnetic dipole.
What?
Magnetic dipole.
We were dealing with magnetic dipole and magnetic dipole moment. In the last class, we had seen yet again the similarities between electric dipole and a magnetic dipole. We had also seen the similarity between a current carrying coil and a magnetic dipole. Everything is similar. We had seen what is the potential energy of a dipole, in which position is the potential energy minimum, stable equilibrium angle is 0. We had seen the work done in rotating a dipole, and we had seen some examples of how we can find out the work done in different cases. Do we remember this? Yes or no?
Yes, sir.
Let me just start this class with this question from JEE Advance. I have seen a repeated trend where they are just repeating the previous year questions. So maybe if you are lucky enough, you might see this question coming in your attempt as well. Let me see if I can put it. Yes, this is the question coming up on your screen now. A current carrying loop is placed in a uniform magnetic field in 4 different orientation, 1, 2, 3, 4. Arrange them in the decreasing order of their potential energies. Arrange them in decreasing order of their potential energies. That is the question. I'll give you 2 minutes to give me the answer. So how are we supposed to do this? You can see in case number 1, the pink case, magnetic field is like this and the area vector is like this. The angle between B and area vector magnetic moment is 180 degrees. Therefore, in this case, the energy would be maximum. Yes or no? In case number 2, magnetic field is still like this, but the area vector of the loop has gone here. The angle is 0. Sorry, the angle is 90. So the potential energy in this case would be 0. In the third case, the magnetic field is like this and the area vector is like this. Angle is acute. So the energy is going to be less. It's going to be negative. So the energy is going to be negative. I can write this is positive maximum. Here the energy is going to be negative. Are you able to understand what I'm writing here?
Yes, sir.
Here the angle between B and the area vector is obtuse, so it is going to be positive but not maximum. Now you can rank them. Number 1 is maximum, then it is number 4, number 1, number 4, number 2, and number 3. So the correct answer has to be option C. Option C is the correct answer. Do we get this, everyone?
Yes, sir.
Yes or no? No, yes.
Sir.
Okay. Let's move ahead. Let me see if I can give you another question on this. Is there any question more on the loop? I've given you this. I've given you this. Okay, this one. This concerns the magnetic moment. We have already discussed it. This is from your previous year papers. And comes the question. This is the question. A square loop is carrying a current I, and the magnitude of the dipole moment is m. If the square loop is changed into a circular loop and it carries the same current, what is the magnetic dipole moment of the circular loop? I'll give you 2 minutes to give me the answer. So how are you supposed to do this? Yes, the loop was a square loop. Let me make that loop for you. The loop was square and then it is converted into a circular loop like this. If I call the edge length of the square as A, and if I call the radius of the circle as R, 4A, which is the perimeter, that will be equal to 2 pi R. Yes or no? So from there I can find the radius of this circle. The radius of this circle will be 4A by 2 pi, or it will be equal to 2A by pi. Do we understand this? Yes or no? No, yes.
Yes, sir.
If I find out the magnetic moment of this loop, the magnetic moment of this loop will be I into pi r square. I into pi r square becomes I multiplied by pi multiplied by 4A square by pi square. So it becomes I into 4 by pi into A square. Yes or no?
Yes, sir.
Now, if I see this I and if I see this A square, I into A square is the magnetic moment of this loop M. Yes or no? Oh, let me call this as M dash. So the magnetic moment of the circular loop M is 4 by pi times the original magnetic moment. So 4m by pi. Here comes the answer. Do we understand this?
Yes, sir.
Yes or no? Everyone understands this? How I got this?
Yes, sir.
Shall I move ahead in life? Hmm.
Yes, sir.
Okay. So we move on. Let me see if I have another question here that can be done of magnetic moment or magnetic loop. No, there is no question as such. So we will move on. And we will move on to the last thing that we need to understand. We have done some bits of it, but we will now do it in more detail. This is known as atomic magnetism. Atomic magnetism. What do I mean by atomic magnetism? Anyone, any idea? What do you mean by atomic magnetism? Now, whenever you have a electron and this electron is actually moving around the nucleus, you remember atomic structure, modern physics, yes or no? This electron is a charge, and this charge is moving around in orbits. This charge moving in orbit makes it current, and because of this charge moving in a circular orbit, it consists of current. It can be treated as a current carrying loop, and therefore it will exhibit all the properties of a current carrying loop. Yes or no?
Yes, sir.
Because of this current carrying loop, this will exhibit magnetism, and this phenomena is known as orbital magnetism. Do we understand this? Yes or no? No or yes?
Yes, sir.
Okay, I'll first listen to what I am saying, and then I'll give you time to write. So if I just draw a very vague diagram of the nucleus and the electron revolving around it would look like this. Yes or no? Ze is the charge inside the nucleus. Z is the atomic number of protons, multiplied by E, this positive charge. And then one electron is moving in circular orbits. Do we understand this? Yes or no? No or yes?
Yes, sir.
Now, you must understand, if such a question comes, that this electron which is revolving will require some what should I say, centripetal force mv square by r, and this centripetal force is given by the attractive force between the nucleus and the charge. Do we understand this? So this first equation is the equation of what? The centripetal force. We understand this? Yes or no? No or yes?
Yes, sir.
Okay. We are doing a bit of atomic structure here also. A bit of atomic structure which is a part of your modern physics. That's why I'm taking it also. Then you must know this orbital angular momentum L MVR, that is always equal to NH by 2 pi. You must have heard this. Yes or no? Where N is your principal quantum number. Have you heard this?
Yes, sir.
Using these two equations, beta, you can find out the velocity of the electron in any orbital and the radius of any orbital. Do we remember this? Do we understand this?
Yes, sir.
That is the basis of it. Okay. Now, moving ahead, since I'll give you time to write, first listen to me, then I'll give you the time to write. Now, since this electron is moving in a circular orbit, you can find out the current, and we have already done this. This current will be Q divided by the time period, charge is E divided by the time period, omega divided by 2 pi. So you can have all these answers for the orbital current. We have already done this. Yes or no? No or yes?
Sir.
Okay. Because of this orbital current or because of electron moving, we have also found out the magnetic field at the center, which is now the nucleus. You can do it in many ways. You can find it out from mu naught I by 2r, or you can find it out by all of these different ways where you have written it in the form of current and in the form of charge. Do we understand this, all the different forms?
Yes, sir.
You just have to remember one form, mu naught I by 2r, and I is E by T or E into F, and you will get all these different forms. Yes, so no, no, or yes. Yes, so no, no, or yes. Are we understanding this, or this is going above our head? Saying bye bye for the last time.
Understanding, sir.
Then one more very important thing that you can see from here. I hope all of you can see this. The magnetic moment of this circular orbit. The magnetic moment of this charge, which is moving in a circular orbit, I into A, you know the value of I, you know A is pi r square, and you can have all these revolutionary formulae coming for magnetic movement of this point charge, electron moving in the circular orbit. Do we understand this? Yes, so no, no, or yes.
Yes, sir.
I'll give you time now. One more thing is left, but it cannot come in the space because the space is all filled up. I'll give you 5 minutes now. Take a deep breath and write all these things. One of these can definitely come in your exam. So we have noted up till here. Now there is a very good relation that you will have to remember, and let me put this relation here. Relation between magnetic moment and angular momentum. Relation between magnetic moment and angular momentum. As you can see, this magnetic momentum MVR, we have seen the formula. If I want, I can write this magnetic moment M also as E into L by 2M. I can write this as E into L by 2M, where L is the angular momentum of this moving electron. If I want to write it vectorly, the magnetic moment of this electron, in the vector form will be minus E into L by 2M. This becomes a very, very important result, not only for this moving electron, but for any body which is rotating and having a charge. So this is the relation between magnetic moment and angular momentum, which is given vectorly. If the charge is negative, they are opposite of each other. If the charge is positive, they are in the same direction. Do we understand this? Do we understand this?
Sir.
Relation between magnetic moment of a rotating body and its angular momentum. If that rotating body has a charge, it will have a magnetic moment as well, and you can find it out from this formula. So for a rotating body, you can write for a rotating body, you can write the relation like this. First listen to me, then I'll give you time to write. The magnetic moment of a rotating body will be q by 2m multiplied by the vector L. No matter what type of body it is. It could be a rotating ring, it could be a rotating disc, It could be a rotating sphere, it could be a rotating cylinder, it could be a rotating hollow sphere, it could be a rotating cone, it could be a rotating hollow cone, doesn't matter. The answer remains. I'll give you 1 minute to note this down. Then you have a, let us say, any rotating body. This is a rotating ring. If someone asks you what is the magnetic moment of this rotating ring, you can simply write this magnetic moment. They won't ask you the vector notation. It's a positive charge, it is moving like this, so you can understand that the magnetic moment will be pointing upwards. The magnitude of this magnetic moment m will be equal to q by 2m, where m is the mass of the body, multiplied by L, angular momentum, and angular momentum is nothing but I into omega. Do you remember this I? Moment of inertia. Moment of inertia of a ring is mr square. We remember this? So in this case, the answer will become q by 2m into m r square into omega. Do we understand this? So the final answer will become q r square omega by 2. Simplest way to find out the magnetic moment of any rotating body. Do we understand this? Yes or no? No, yes. Do we understand this, bacho?
Sir.
Now, what I'm giving you is a table. It's a table of all these common rotating bodies with their moment of inertia and their angular momentum. It is just a revision of what we have already done. So I will ask you to kindly note it down. Okay, then let us move and solve some question based on this chapter. We'll try to solve whatever type of questions are coming in the exam these days, and I'm sure one of these question will be there in your paper. You've done a lot of questions of this type. This is questions taken from your very recent papers from 2020 to 22 onwards. A proton, a neutron, and an alpha particle are moving with the same momentum in a uniform magnetic field. The ratio of magnetic force on them and their speed is. I'll give you a minute to give me the answer. You are just supposed to find out the ratios. They are proton. If I call the mass of a proton as m, what will be the mass of a neutron? Tell me that. What will be the mass of a neutron? If I call the mass of a proton as m, what will be the mass of a neutron? Yes. No one knows it? It is 2 times of m. A neutron consists of 1 neutron and 1 proton. Then what will be the mass of an alpha particle? I gave that to you. Do you remember it? What will be the mass of an alpha particle then?
4m.
It would be 4m. Very good. If I call the charge of the proton as P, what will be the charge of a neutron? It would be P only. It only has 1 proton. What will be the charge of an alpha particle?
P.
4 times P. It's a helium nucleus. So, I always write 4 times. 2 times P. Last time also I write 4 times. 2 times P. Once you understand this, the rest is pretty simple. I have to find the ratio of forces. Force acting on a charged particle is Q, V, B, sine theta. Everything is same. Sin theta is same. B is same. Now, if you talk about speeds are different, but momentums are same. So you can write this speed as momentum, which is same, divided by mass. So my force will come proportional to Q by M because they have the same momentum. Do we understand this?
Yes, sir.
Well done, sir. Then force on a proton is to force on the neutron is to force on the alpha will be equal to P by M is to P by 2M is to 2P by 4M. So what is the ratio coming? What is the ratio coming of the forces? Ratio of the forces. Ratio of the forces. The ratio of the forces is coming 2 is to 1 is to 1. As soon as you get this, there is one option only which has this correct one, and that is option number 2. So, my dear friends, option number 2 is the correct answer. I'll give you 2 minutes to note this down. So, please be very attentive with these questions. I'm doing very selective questions now. The questions which can definitely come in your exam, and this is a revision of the entire chapter that we have done. A very important chapter which is getting a lot of question these days. So since this is the last class, we are doing a revision. This is the next question. Magnetic fields at 2 points on the axis of a circular coil at a distance of 0.05 and 0.2 meters from the center are in the ratio 8 is to 1. What is the radius of the coil? I'll give you 2 minutes to give me the answer. Can you tell me how did you try this question, beta? Would you like to tell me how did you try this question?
Magnetic field equals to mu naught I by 2 into r square by x square plus r square whole power 3 by 2 using that formula.
Yes, that's it. From there you will get magnetic field P is equal to mu naught I by 2 times r square upon r square plus x square raised to the power 3 by 2. That's it. That is what you need to apply. Nothing else. You just have to take the ratio then. B1 by B2 will be equal to everything will get cut. B1 by B2 is 8 by 1. That will be equal to R square plus 0.05 square divided by R square plus 0.2 square raised to the power of 2 by 3. Sorry, 3 by 2. From here you have to solve and get the value of R, and the value of R that I am having as answer is option B, 0.1. That's the answer that I was looking at. That is the answer that I was looking at. Well, if you remember, I also probably gave you a shortcut to remember this, but no one seems to recollect this. I gave you a shortcut when the ratio was given. Let me go back and see if I remember it correctly. Given you the formula. And I hope that you have written it down somewhere. in some of their notebook from where you can extract it and use it. It doesn't look like you remember it. Maybe I'm mistaken and I did not give you that formula. See, we had seen this formula B center by B axis 1 plus x square by r square at any point if it is same time. Same thing here. You just remember this formula and use them when it is required. That is what it's requested from you. Everyone understands this? Yes or no? So just remember these simple things and you would be doing good. This is again the next problem from this past 3 years paper and it is coming on your screens now. A hairpin like shape as shown in the figure is made by bending a long current carrying wire. What is the magnitude of magnetic field at point P which lies at the center of this semicircle? I'll give you 2 minutes to give me the answer. So magnetic field due to all the three wires are going to get added up because of this wire and this wire. Magnetic field is mu naught I by 4 pi r. They will get added up, so multiplied by 2 plus field due to a semicircular loop of wire is mu naught I by 4r. All the fields will get added up and the answer, my dear friends, that you are going to get is option number B. That is the correct answer, my dear friends. I'll give you 1 minute to note it down. Okay then, let's move ahead and give you this question. I hope you can at least give me the answer for this question. A loop of flexible wire of irregular shape carrying current is placed in an external magnetic field. Identify the effect of the field on the wire. I'll give you 2 minutes to give me the answer for this one. It will obviously assume a circular shape, any shape wire. It will assume a circular shape. Yes or no?
Yes, sir.
What will be the plane of this loop? Will it be parallel to the field? It can never be parallel to the field because it will experience force in the perpendicular direction. The loop would be normal to the field. As you could see, the example that I gave you a random loop like this. And my dear friend, the magnetic field was inside and the loop was on the xy plane. So it is perpendicular to the magnetic field. Plane is perpendicular to the magnetic field. Please remember this, bacha. Please remember this. I urge you, please remember this. Simple things shall do great. The next one coming up, my dear friends. Question from recent years. And you can see almost all of the questions we have done in the class. This is the next one in line. A deuteron and an alpha particle having equal kinetic energy enter perpendicular into a magnetic field. Rd and R alpha are the respective radii of circular path. Ratio you have to find out. Okay, I will do it. Radius is mv by qb, or it was under root of 2mk by qb. So radius of the deuteron divided by radius of alpha particle, my dear friend, will be equal to root over mass of deuteron divided by mass of alpha particle multiplied by the charge of the alpha particle divided by the charge of the deuteron, my dear friends. Mass of the deuteron by mass of the alpha particle is 2 by 4 multiplied by charge of the alpha particle divided by the charge of deuteron is 2:1. The ratio, my dear friend, is coming as root 2. Root 2. That is the answer that we are looking at, my dear friends. That is the answer that we are looking at, my dear friends. Please be careful. 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 And please be careful. That is all I can ask for right now. Just be careful and nothing else. I'll give you one more. Let's see how you go about this. Same question you are going to see in your examination hall, bacha. 4 days from now. 4 days from now. Exactly 4 days from now. 4 days from now, you'll see the same question in the examination hall. 4 days from now, you'll see the same question in the examination hall. 4 days from now, you will see the same question in your examination hall. I'll wait for 2 minutes for you to give me the answer. Option 2 is the correct answer. Well done. You see, I always keep on telling you, students are like cash vouchers. Sometimes the cash voucher may not work. That does not mean that the cash voucher is wrong. That means the person who has put the code was wrong. MV by QB. Two ions have the same mass, so M goes away. Charges ka ratio is given. Uniform magnetic field is 7. So R is proportional to V by Q, my dear friends. So R1 by R2 will be V1 by V2 into Q2 by Q1. And the answer I think that you get is 4 by 3. Well done. Anyone got this? Yes or no? No, yes.
Yes, sir.
Huh? Chalo. Revision time, my dear friends. Revision time. Comes the question here. JEE advanced. And you have 2 minutes to give me the answer for this one. Option 1 is correct. Anyone knows how to solve this? Yes or no? You understand this, or do I need to do the needful? You understand this, no? Yes, sir, or no, sir?
Yes, sir.
Okay. Let's see how you do with this one. Revision time. One of the last questions that you are going to see before the exams. Two ions of masses 4 AMU and 16 AMU have charges plus 2E and plus 3E respectively. These ions pass through their region of constant perpendicular magnetic field. The kinetic energy of both ions is same. Then, which is the correct option? You have 2 minutes to show your talents, else I will show mine. Option 2. And that is absolutely correct. Well done. Radius is 2 pi k ka root divided by QB. So radius is proportional to root over M by Q. So R1 by R2, if you find out, that will come M1 by M2 ka root multiplied by Q2 by Q1. It will come as 3 by 4. The radius of the lighter ion is less than the radius of the heavier ion. Do we understand this? Yes or no? Yes or no?
Sir.
Therefore, what do you mean by deflection? What do you mean by deflection? What do you mean by deflection? The question says that they will be deflected. They pass through a region of constant perpendicular magnetic field. So they pass through this region, something like this. They enter here and they go and get deflected like this. Now, this is the center O, this is the radius R. Now, if you talk about the deflection, they get deflected by some angle theta. The sine of this angle theta is d by r. It is inversely proportional to r, and therefore the ion with the ion with the smaller radius will get deflected more. Do we understand this? Yes or no? No or yes?
Yes, sir.
Okay, great. I'll give you one last question and then these questions are coming a lot of times, and I hope that you will get one question 4 days from now. A proton and an alpha particle, 3 particles normally come: proton, neutron, and alpha particle. With their masses, so is everything at the masses in the ratio 1:4 and charges in the ratio 1:2 are accelerated from rest through a potential difference V. If a uniform magnetic field B is set up perpendicular to their velocities, the ratio of the circular paths described by them will be in what ratio? I'll give you 2 minutes to give me the answer. We all know radius is root over 2 mk by qb. Kinetic energy can be written as q into the voltage divided by qb. So I can say radius r1 divided by radius r2. Everything else is same. It will be proportional to m1 by m2 multiplied by q2 by q1. Do we understand this? When you put the values, radius of proton divided by radius of the alpha particle, I think you are going to get this answer. Answer A, 1 is to root 2. Do we understand this? Yes or no? We understand this? Well, that takes us to the end of this class and end of this session also. We could complete as much as we could, and I wish you all best of luck for your exam, for your first attempt. Remember, it's just an attempt. Go there, try your best. At the end of the day, it's just an exam. So I'll see you after your exams, and I hope that you can do your best in the exams. And don't worry, whether whatever you do in your life, this exam is just an exam. It's just a day in your life. It's just 3 hours of your life. It will come and it will go. And after some time, you will not even remember this day also. So take care. Take good care of your health and give your exams in the best possible way. Bye bye.
Sir.